Hi, this is our last video about similarity and diagonalization. So we were actually talking about all about similarity and diagonalization. This is our third video. So we continue from here. We have another theorem. Says that let A be an m by n matrix and lambda 1, lambda 2, dot, 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 lambda k be distinct eigenvalues of A. So that means all of these eigenvalues are different. None of these two are equal to each other. If this Bi is a basis for the eigenspace E lambda I, lambda I, then the union of these bases, B1, B2, dot, 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 Bk, the total collection of basis vectors for all of the eigenspaces is linearly independent. All right, so here, just when we are dealing with this kind of matrices. So here, for example, we are given matrix A, and we know how to find actually the eigenvalues and also corresponding eigenvectors. And actually for each eigenvalue, and also actually you have eigenspaces. Now we are just saying that if you just combine all of these vectors, they form a kind of set. And is here we are claiming that all of these vectors in a set are linearly independent. Okay, let actually this bi contains these vectors bi1 bi2 dot 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 bi and I. I'm just using here ni because here I don't know how many different bases do we have. That's why subscription notation is much better. Otherwise we need to use a lot of letters. So we have to show that these vectors, this v11, v12, v1n, what are these? Actually, these are basis vectors of the first basis, right? B1. And this one is the basis vectors of the second eigenspace. And these are the basis vectors of, let's say, k's eigenspace. So we are going to show that actually these vectors are linearly independent, right? Because here we have, well, eigenspaces here, one, maybe two, dot, dot, dot. Here we have k. Let's say this one is the first one, and this one is eigenspace corresponding to lambda 2, dot, dot, dot. This one is eigenspace corresponding to lambda k, right? And actually, this set actually is spanned by these vectors v11, v12, v1n. Since we know that it's a basis, that means that these vectors v11, v12, v1, and 1, these are linearly independent, right? And also here, E lambda 2, it means this v21, v22, v2n2. These are the vectors here, these are here, and they are also, since they form a basis, also they are linearly independent. And also here we are claiming that if you just combine all of these vectors, still they form a linearly independent set. Okay, so now here, suppose some non-trivial linear combinations of these vectors is the zero vector. So here, non-trivial with C11 times V11 plus C12 plus times V12 plus dot dot. Here, these are the linear combination of the basis vectors of the first eigenspace. And the second, in the second brackets, these are just linear combinations of the basis vectors of the second eigenspace. Dot dot dot. Also in a similar way, the last one. Okay, and here at least one of these coefficients is not equal to 0 because we're hoping that actually we're assuming that they are non-trivial. Okay, now if you just denote these sums, let's say the first sum by x1 and the second sum by x2 and the last sum here dot dot, we have a lot of vectors here, let's say xk. Now, what we have here then? Here we have x1 plus x2 plus dot 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 and plus xk. On the right hand side, we have a zero vector, right? So now we know that each x1 is, for example, x1 is a vector from ei1, right? x2 is a vector from ei2. xk is a vector from eik. For example, here, this x1 is a kind of vector taken from here. This x2 also a vector from here. And the last one is a vector from here. Okay. And so either is an eigenvector corresponding to lambda I, right? Or that's equal to 0. Yeah, because we know that actually eigenspace it is a subspace, right? Also, it contains 0 vector. So this x1 either it is an eigenvector or it is 0 vector, because with a 0, it cannot be eigenvector, right? For example, if this x1 is equal to 0, right? Since we know that all of these vectors v11, v12, blah, 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 v1, n1, actually these vectors are linearly independent because they form a basis. That actually forces that all these coefficients must be equal to 0. Actually, the similar scenario actually works for the second one and the case one. So actually this x1, x2, xk, if all of these vectors are zeros, then automatically all of these coefficients are 0, which proves that all of these vectors are in the set B, all of these vectors are linearly independent. And how about the second case? And here, if x1 is an eigenvector, but if it is an eigenvector, then if okay, if eigenvector, now here we have like this. Here we have a x1 is equal to lambda 1 x1 if it is an eigenvector. For the second one, a x2 equals lambda 2 x2 dot dot a xk is equal to lambda k, and here we have xk, right? And here in the theorem, they are saying that actually they are distinct. And actually, we have just already studied the theorem that if these lambdas are distinct, then this x1, x2, xk, they must be linearly independent, right? Actually, here, this relationship, right, shows that actually that is linearly dependence relationship, right? As you see here, this x1, if you just take everything to the right-hand side, we are expressing this x1 as a linear combination of the remaining vectors. And there's a contradiction here. That means that actually these vectors cannot be this x1, x2, xk, they cannot be linearly dependent. So this x1, x2, xk, then they are linearly independent, which means that all of these vectors in the set B, they are linearly independent. Okay. Here, another theorem. If A is an m by n matrix with n distinct eigenvalues, then A is diagonalizable. But if you're talking about 2 by 2 matrix, and if we have two different eigenvalues, then immediately we can just actually say that then it is diagonalizable. Then we can try to find the diagonal matrix. All right. For example, the matrix here, what are the actually, as you see here, it's an upper triangular matrix, and here we can just find the eigenvalues directly from here, because all the components in the main diagonal, they are just eigenvalues of this matrix. So lambda 1 is 2, lambda 2 is 5, and lambda 3 is -1. You see here, all of these numbers are different, they are distinct. That means that this matrix is diagonalizable. And once we know that, then actually we can just try to find the diagonal matrix. So another lemma, also we'll just have a look at this and the proof. If A is an m by n matrix, then the geometric multiplicity of each eigenvalue is less than or equal to its algebraic multiplicity. So actual geometric multiplicity, we know that geometric multiplicity is the number of vectors in each eigenspace, right? Actually, the basis vectors. And is saying that actually this is always less than or equal to algebraic multiplicity. You can just see one examples of this thing in the next example. That's the last theorem of this session. If A is an m by n matrix and whose distinct eigenvalues are lambda 1, lambda 2, lambda k, the following statements are equivalent. Now you're familiar with this concept. When we say equivalence, if one is true, all of these facts, actually statements, must be true. If one is not true, then none of them is true. So it's saying that if A is an m by n matrix whose distinct eigenvalues are lambda 1, lambda 2, lambda k, A is diagonalizable. If it is diagonalizable, then the union B of the basis of the eigenspace of A contains n vectors. Then if it is true, then the algebraic multiplicity of each eigenvalue equals its geometric multiplicity. We will see them in example. For example, if you consider this matrix A, here eigenvectors, eigenvalues, these are not vectors, eigenvalues, lambda 1, lambda 2 equals 1, and we know how to find this, right? If in that actually we got this, and lambda 3 equals 2. And here, algebraic multiplicity of this eigenvalue, right, is equal to 2 because it appears twice in the equation. And this one, algebraic multiplicity of this eigenvalue is 1. So now, if you just find the eigenspace corresponding to this eigenvalue, and here we have only one basis vectors here. So which means that dimension of E1 is equal to 1, which is the geometric multiplicity of this eigenvalue. So here that is 2. Let's see, here it is 1. Actually, that means that they are not equal, right? So now from here we can say that actually this matrix is not diagonalizable. Why? Because if it is diagonalizable, here for each eigenvalue, its algebraic multiplicity must be equal to the geometric multiplicity of that eigenvalue. Consider another matrix here. If you just find the eigenvalues here, actually I don't know why I put eigenvectors, it should be eigenvalues. So lambda 1, lambda 2 is equal to 0, and lambda 3 is equal to negative 2. Okay. So example 8. Okay, and also actually it has two distinct eigenvalues. Right? The first one is 0, the second one is negative 2. So here 0, it has the algebraic multiplicity is 2, and the lambda 3 algebraic multiplicity is 1. So if you just find the eigenspace corresponding to this eigenvalue, the first one is 0. Here we have two vectors. That means dimension of E sub 0 is 2, right? So that's equal to 2. Since the eigenvectors lambda 1 equals lambda 2 equals 0 and has algebraic multiplicity 2 and geometric multiplicity 2, because here we have two vectors, and lambda 3 equals negative 2 has algebraic multiplicity 1 and geometric multiplicity 1, so A is diagonalizable. Anyway, that's the use of that theorem. So we have two more examples here, and I will finish this chapter with these examples and just make use of this diagonalizable matrices to calculate this matrix. Here it says that computes a to the power of 12 if A is this 2 by 2 matrix whose components are 0, 1, 2, 1. And the matrix A has eigenvalues, lambda 1 equals negative 1, and lambda 2 equals 2, with corresponding eigenvectors, v1 equals 1, negative 1, and v2 equals 1 and 2. Okay. So to do this one, since these eigenvalues are distinct, right? It means it is diagonalizable. So which means that here I can just write it as A times P equals P times D, right? Or it can just write here we have A that is 0, 1, 2, 1, right? And what is P? Actually, P are the columns of P are these eigenvectors. The first one is 1, negative 1. Second one is 1, 2. And here we have also P, 1, 1, minus 1, 2. And here we have diagonal matrix. Here V1, so here we have lambda 1. Lambda 1 is negative, lambda 1 is negative 1. Here we have 0. Lambda 2 is 2. Okay. Anyway, so how do you calculate this A to the power 12? Now, since it is so, also actually that thing, if you just multiply both sides by the inverse of P on the right, you can just write this A as P times D times P inverse. Okay, so here, okay, we're going to get calculate this a to the power 12. First, what is a squared? A squared is p d p inverse is multiplied by itself, p d p inverse. So if you evaluate this, p inverse times p, that is identity matrix, d times d squared, so is equal to p times d and p inverse. And how about a cube? A cube is a squared times a. A squared is p d squared, actually it's squared. And here we have p inverse and multiply by a, which is equal to p d and p inverse. And which is equal to, if you evaluate this, if we have p and p inverse times p, that is just identity matrix, d squared times d, that is d cubed, and here we have p inverse, right? So as you see here, there's a pattern here. Every time actually this in the middle we have p inverse p, it just disappears. Actually, that's equal to identity matrix, right? It has no effect. So now I can just write here then a to the power of 12, and that's just equal to p times d to the power of 12 times p inverse. Okay. So what is the inverse of p? So I should just know this inverse of p, right? And after we can calculate this diagonal matrix. So let me just evaluate here. P inverse is equal to, its determinant is, where is p? This one is p. Actually, this one is p. P inverse is 2 minus minus 1. That's equal to 3. So here there's 1 over 3. Right? And the a, we should interchange this. Here we have 2 and 1. Multiply b and c by negative 1. So here we have 1 minus 1, which is equal to 2 over 3 minus 1 over 3. Actually, so let's see, just right here. That is equal to, even I can just keep it like this. Okay, that's equal to 1 over 3 this. Okay. That's our P inverse. All right. So now if you evaluate this, here we get a to the power of 12 equals p. P is, here we have 1, 1 minus 1, 2 times d to the power of 12. How we calculate this to the diagonal matrix to the power of 12? Just we need to raise to the power of 12, each component in the main diagonal. Here this one is d, right? This one is d. D to the power of 12 will be, here we have minus 1 to the power of 12. Here we have 0, 0, 2 to the power of 12. And here we have P inverse, which is equal to 1 over 3 times T2 minus 1, 1, 1. And 1 over 3 is just a constant. It's a scalar. I can just keep this here, 1 over 3. First, if you multiply these two matters together, so here we have 1, 1 times 1, 1, 0 times 1, so here we have 1. 0 times 1, 0, 2 to the power 12 times 1, here we have 2 to the power of 12. Now, negative 1 times 1, it is negative 1, 0 times 2, so here we have negative 1. 0 times negative 1, 0, 2 times 2 to the power of 12, that is 2 to the power of 13. And here we have 2 minus 1, 1, 1. Okay, one more step equals, here we have 2 times 1, 2, 1 times 2 to the power 12. So here we have 2 plus 2 to the power 12. And negative 1 times 1, it is negative 1. Here we have negative 1 plus 2 to the power of 12. And here we have negative 2. So negative 2 plus 2 to the power of 13. Minus 1 times minus 1, it is 1. 1 plus 2 to the power of 13. Okay. So we can just simplify and write the answer. So that's equal to, let me just write here, 1 over 3. And here we have big numbers. And just evaluate this to the power 12. And here we have another number. Okay, here we have 2 plus 2 is the power of 12. That's equal to 4098. 4098. The second one is minus 1 plus 2 to the power of 12, which is equal to 4095. And here we have minus 2 plus 2 to the power of 13, which is equal to 8190. And the last one is 1 plus 2 to the power of 13. That's equal to 8193. Okay. And I can just bring this 3 inside. I don't know if you just divide these numbers. 4098 is divided by 3. That is 1366. And 4095 is divided by 3. That's equal to 1365. And 8190 is divided by 3. That's equal to 2730. And 8193 is divided by 3. That's equal to 2731. That is how we evaluate the power of A using this diagonalization method. Okay, we have the last example. Compute B to the power of 10 if B matrix is equal to this. So now, again, the steps are clear. First, we need to find or identify the eigenvalues of this matrix. To do this one, first, we need to form our, get right the characteristic polynomial of this matrix, which is equal to determinant of B minus lambda I. That's equal to minus 5 minus lambda. Here we have minus 4, 8, 7 minus lambda. So now, if we just solve this equation, which is equal to evaluate the determinant, we get lambda squared minus 2 lambda minus 3. It's just a quadratic equation, and the factorize this, that's equal to 0, right? And that's equal to 0. If you solve this, the first row will be negative 1, and the second one is 3. So the lambda 1 equals negative 1, lambda 2 is 3. So now we have to get the corresponding eigenvectors, right? So when lambda 1 equals negative 1, if we just substitute here, this homogeneous system, here we have minus 4, right? Because minus 5 minus minus 1 is minus 4. Here we have minus 4, 8, 7 minus minus 1 is 8. So that's our augmented matrix. If we just reduce this to reduced rational form, we have this matrix. And also in a similar way, when lambda 2 equals 3 and solve that homogeneous system, B minus lambda I times X is equal to 0. And just reduce this to reduced rational form, we have 1 minus 1 and 0, 0. So now we got eigenvectors. One eigenvector corresponding to this eigenvalue, negative 1. Here we have 1, 2, right? Because here we have x1 minus 1 over x2 is equal to 0. That is one eigenvalue. Another one is for lambda 2. Again, here we have x1 minus x2 is equal to 0. So one eigenvector corresponding to this eigenvalue is 1, 1. Okay. So now we have to evaluate that thing, right? Again, we know the formula to evaluate this B, right? Because we know that actually it is diagonalizable. So we can just write it as B times, here we have, maybe I can just write here, equals P times dP inverse, right? What is P? Actually, these are just columns of PR, V1 and V2. Here we have 1, 2, and 1, 1. And what is D? Here we have lambda 1. Lambda 1 is negative 1, 0, 0, lambda 2. That is 3. But make sure that actually you're writing this in the right order. And here we have the inverse of P. That is 1, 1, 2, 1, inverse. Okay. So from here, let me just evaluate P inverse. P inverse equals, its determinant is 1 minus 2. That's equal to negative 1. And here, if you just interchange this, it is 1 and 1. So here we have minus 2, minus 1, and 1, which is equal to negative 1, 1. Here we have 2, negative 1. Okay, so here now we need to evaluate b to the power of 10, which is equal to p times d to the power of 10 times p inverse. And matrix P is just here we have 1, 2, 1, 1, and D to the power of 10. So here we have D. Where is it? It's here. Minus 1 to the power of 10. That is 1, 0, 0. 3 to the power of 10. That is 3 to the power of 10. And here we have P inverse, which is equal to negative 1, 1, 2, minus 1. Okay, just now, we need to evaluate this. That's equal to the first one. If you just multiply the first two matrices, 1 times 1, 1, 0 times 1, 0. So here we have 1. 0 times 1, 0. 1 times 3 to the power of 10. Here we have 3 to the power of 10. And 2 times 1, 2. 1 times 0. So here we have 2. And it is 0. Here we have 3 to the power of 10. And here we have negative 1, 1, 2, minus 1. And which is equal to minus 1 times 1 minus 1. So here we have minus 1 plus 2 times 3 to the power of 10. And here we have 1. Here we have 1 minus 3 to the power of 10. And second row by the first column, here we have minus 2 plus 2 times 3 to the power of 10. And here we have 2 minus 3 to the power of 10. And you can just evaluate this and write the answer. That is how we use, that's a theorem to calculate this kind of matrix. It has some different also applications. These are just two examples. And that's the end of this section. Okay. So thank you very much.